This video cast is about Chapter 15, Equilibrium. Equilibrium tells us that reactions are reversible. Not only do reactions go from reactants A to products B, but they also go from products B to reactants A at the same time. And so we can write this reaction as A double arrow goes to B. But how much does this happen? Does all of A go to B and you're just left with a minuscule amount of A? Or does only half of it go to B? Or does only a tiny bit become B and there's very little bit of this and there's a lot of the reactant left over? That's what this chapter helps decide, is how much. And we can calculate using something called the equilibrium constant, how much product and how much reactant we get. First, a couple of definitions. Now remember, when we write chemical reactions, we always write them from left to right. And we always call the thing on the left side the reactants, no matter what the arrows are, left, right, up and down, sideways. These are always called the reactants. And these guys over here on the right side are always called the products. This is reactants, this is products. It doesn't matter if we have a single arrow or a double arrow like this. Always remember that reactants are on the left and products are on the right. So what is this thing called the equilibrium constant? And what is this thing called equilibrium? Well, take a look in your packet at the equilibrium practice problems used in the Chapter 15 video cast. Pause the video now if you don't have these out and make sure you have them in front of you. They're in your PowerPoint packet. Question number 1 says, given the reaction A goes to B, find the equilibrium constant if A goes to B and B goes to A have rate constants of 4 times 10 to the negative 2 and 2 times 10 to the negative 2 respectively. So what this is saying is that we have a reaction of A going to B with a rate constant in the forward direction. I'll put a little f down there, meaning that it's in the forward direction, of 4 times 10 to the negative 2. I'm going to ignore units for right now, as we'll find out we do a lot in this chapter. And we have the reverse of this reaction, B goes to A, having a reverse rate constant. I wrote this reaction in reverse now of what this way is written, as 2 times 10 to the negative 2. Well, the equilibrium constant that tells us is there more A or is there more B is actually defined as the forward rate constant divided by the reverse rate constant. And right now is the time to get used to what all these K's mean. The equilibrium constant is always written as a capital K and occasionally has a small letter down below here denoting whether it comes from concentrations, pressures, solubility, and even some other things that we'll learn in acids and bases. The rate constants that we learned about in Chapter 14 are always small or lowercase k's, and the little f and the little r just mean if the reaction is in the forward direction or the reverse direction. When you calculate the equilibrium constant using the forward and reverse rate constants, you take the forward rate constant, 4 times 10 to the negative 2, put it on the top, and take the reverse rate constant, 2 times 10 to the negative 2, and put that on the bottom. Notice how the times 10 to the negative 2's cancel out, and now we have 4 divided by 2, or 2, as our equilibrium constant. Well, we can go on and we can write this more generally for any reaction by using the definition of K sub C called the law of mass action. And in number 2, it says, write K sub C, or write the equilibrium constant K, for the reaction 3NO goes to N2O plus NO2. And the general definition for writing the equilibrium constant is that it is products, concentrations, or pressures. Remember, both can be used, or they can be used together to the power of its coefficient or coefficients, and if there's more than one product, you multiply them together, divided by the reactants. And once again, it's the concentrations or the pressures, depending on what it is, to the power of its coefficient or coefficients. If there's more than one, you multiply those together down here as well. It's always products on the top, reactants on the bottom. And remember, when you get a numerical value for K, say, for example, the numerical value is 100, it's always considered to be 100 divided by 1, meaning there's lots of products and less reactants. If you get a big number like this, it always means there's lots of products and very few comparative reactants. If you get a number less than 1, like, say, for instance, 1/10 or 0.1, that means that there's lots of reactants or lots more reactants and very few products. That's how K can tell us whether there's lots of A or lots of B in a reaction like this. If it's a big number, that means there's lots of products. If it's a number smaller than 1, that means there's lots of reactants. There'll never be a negative number. It'll always be a number either the bigger than 1 or smaller than 1. What happens if K is equal to 1? Well, that means that the products and reactants have the same concentrations. Just because we're not at 1, though, does not mean we're not at equilibrium. We can have big numbers or small numbers for equilibrium. Enough on that. Let's write the equilibrium constant expression for this equation. Notice the products are N2O and also NO2. And they each have a coefficient of 1 in front of them, so I could write a small 1 up here, meaning that that's their coefficients. Divide it by the reactants. And the reactant here is NO. So put NO down below. And notice it has a 3 in front of it, so raise it to the third power and put a power of 3 below it. This is equal to the equilibrium constant in terms of concentrations, so we put a small c below the capital letter K. Make sure you have a capital letter K for equilibrium constant. Now notice this. I'm going to write it a big square around it because a lot of these questions, 3, 4, 5, and 6, are all based on being able to recognize this makeup of this equation's equilibrium constant. Notice the products on the top, the reactant on the bottom to the third power. Let's move on to number 3. If K sub C is equal to 2.3 times 10 to the 5th, does the reaction favor NO or N2O? Well, take a look. Take a look at the reactants and the products here. They're telling us K sub C is a really big number, 2.3 times 10 to the 5th. That means I could write it as 2.3 times 10 to the 5th over 1, a fraction just like this. That means 1 would be the NO down here, and the 2.3 times 10 to the 5th would be a big number up here. So what's favored? Well, the thing with the bigger number, of course. So that means N2O and NO2, or the products right here, would be favored, and there would be lots of N2O, or I could just say products, because the number is really, really big. The next 3 questions are examples of how K changes when a reaction is reversed, a reaction is multiplied or divided by a coefficient, or 2 or more reactions are added together. And we'll still use this same reaction up here with the NO, the N2O, and the NO2 to illustrate how these changes take place. So we'll be referring back to this quite a bit. The first question says, what is K sub C for N2O plus NO2 going to 3NO? Notice this reaction is simply the reverse of the reaction we had up here. It's this reaction written backwards. Notice the N2O and the NO2. Here's the N2O and the NO2. If I wrote the equilibrium constant expression for this one, K or K sub C, it would equal products NO to the third power divided by the reactants N2O times NO2. Okay? Notice these are now the products, this is now the product, and this is the reactant. Look at this versus what we had written up here. What has changed? Notice the NO used to be on the bottom or in the denominator up here. Now it's in the numerator. Notice these two right here used to be on the top, and now they're on the bottom. In other words, the reverse of the reaction, the reverse of the reaction's equilibrium constant is merely the reciprocal or the inverse of the equilibrium constant the other direction. So when it asks what is K sub C or what is the equilibrium constant for the reverse of a reaction, all you need to know is that it is the 1 over or the reverse of the equilibrium constant of the other direction reaction. Now it told us up here that K sub C for the reaction in this direction right here was 2.3 times 10 to the 5th. We now took this reaction and wrote it backwards or in reverse, making these the reactants and these the products. And remember, it doesn't matter what arrows are in here, it's only what's written on the left that's reactants and what's written on the right as products. So we need to take the 2.3 times 10 to the 5th and find the inverse of that. This would be 1 over 2.3 times 10 to the 5th, and if you chunk that into your calculator, I believe it turns out to be 4.35, I think I rounded a little bit, times 10 to the negative 6th. And don't worry about units for the equilibrium constant. As a matter of fact, the cool part about equilibrium is that you never have to worry about units for the equilibrium constant, because really it's based on something called activities rather than concentrations, even though the concentrations are quite close to what the activities actually are. Anyway, not to concern you about it too much, because you don't have to put units on it. Cool deal, huh? Number 5. What is K sub C for? Notice this reaction now. And you can see that this reaction, compared to the one above it, have something very, very much in common. We still have the N2O, but notice there's a 2 in front of it now. We still have the NO2, but notice there's a 2 in front of it now. And we still have the NO, but now we have a 6 in front of it instead of a 3. What has happened to gain this reaction versus the one up above? Well, what we've done is we've taken this reaction up above and multiplied it by 2. We've taken and multiplied it by 2, putting a 2 in front of the N2O, a 2 in front of the NO2, and now we have 3 times 2, or 6, in front of the NO. If I wrote the equilibrium constant expression for this, it would now look like products NO to the 6th power, because there's a 6 here, divided by N2O to the 2nd times NO2 to the 2nd. And for those of you that love math, watch this. This is the same as saying NO to the 3rd divided by N2O to the 1st times NO2 to the 1st, and then taking this whole thing and squaring it. Oh, when you square something like this, remember you would distribute or take this power and multiply each of them by 2. The cool part is, though, look at this part that's inside the parentheses that I'm circling in blue. This is exactly the same as this, except we've squared it. So what that means is if you multiply a reaction by some number, in this case we multiplied it by 2, you simply take the equilibrium constant, which I'm circling in blue right here, and raise it to that power. So if you multiply a reaction by something, raise it to that power. So to find K, we can take the K that we found up above, 4.35 times 10 to the negative 6th, and raise it to the power that we multiplied this reaction by. We happen to multiply this reaction by 2 to obtain this new one right here. And so I'll take and I will square this to get my new equilibrium constant. And that turns out to be 4.79. Whoops. Oh, sorry. Wrong number. 5.3 times 10 to the 10th. Oh, shoot. I think I did that one wrong. I think I've got the wrong answer on top there. But anyway, we take this, and it would be 4.35 squared. And then we would take, and it would be times 10 to the negative 12th, I believe, as well. Let's see, 4.35 squared. I can do it in my calculator really quick. Notice it's times 10 to the negative 12th. 4.35 would turn out to be about 19. So I'd end up with 19 times 10 to the negative 12th, or 1.9 times 10 to the negative 11th or so for my equilibrium constant there for 5a. Now let's take a look at 5b. 5b. What is k sub c for 1/2 times N2O3 times 1 plus 1/2 NO2 goes to 3/2 NO. Now take a look and notice how this reaction is similar to the one we had up here again. Notice this time we only have 1/2 N2O. We only have 1/2 NO2, and we only have 3/2 of NO. In other words, what we've done is we've taken this reaction up here and multiplied it by 1/2. Multiplied it by 1/2 to obtain this reaction down below. So if I multiplied by the reaction by 1/2, guess what I have to do to the equilibrium constant? I have to take this equilibrium constant now for this reaction and raise it to the power that I multiplied it by. The power that I multiplied it by, or the power that I would raise it to, is to the 1/2 power. So I would write it as 4.35 times 10 to the negative 6th raised to the 1/2 power, or for those of you that are kind of mathematical minded, the 1/2 power is also known as the, yep, you got it, square root. So I would take the square root of 4.35 times 10 to the negative 6th, and I end up with approximately 2.08 times 10 to the negative 3rd as my equilibrium constant for this reaction, because this reaction was simply multiplied by 1/2 compared to this. So to summarize, first of all, up here in number 4, if you have the reverse of a reaction, you take the reciprocal. Okay, reciprocal, if it's reverse. Reverse equals reciprocal. In A and B, if you multiply a reaction by a number, you simply raise the K to that power, to the power of that number. You raise the K to the power of that number. Now take a look at the next page. The last problem in this series of what happens when you change things. Remember, reverse is reciprocal, multiply by a number, you raise k to a power. And take a look at number 6. Number 6 does something a little bit different. It has 2 reactions. And it says, what is the overall reaction given these 2 steps? And then it says, calculate k sub c for the overall reaction. So we have 2 reactions right here, and we're going to add them together. Now, to do that, take the reactants on both sides and put them together. O2 plus 2O plus 2H2 goes to, on this side now we have 2O plus 2H2O. Okay? There's our combined overall reaction. Now you might say, oh, but I could cancel these O's. Let's just leave them in there for right now. We will cancel them later. Well, let's just leave them in there for right now. Okay? And then it says calculate K sub C for the overall reaction. Before I do that, I want to go back to these two reactions up here, and I want to write K sub C for each one of them. For the top reaction, the K sub C, or the K, equilibrium constant, is products O to the second power divided by O2 to the first power. For the bottom reaction, K is equal to H2O to the second power divided by O to the second power times H2 to the second power. Okay? Those are my equilibrium constants for the top and the bottom reaction. Now let's write the K for the overall reaction that we wrote up here. The overall reaction we wrote up here. Now it would be equal to products, which is O to the second power, times H2O to the second power, because there's a 2 right here, divided by O2 times O raised to the second power times H2 raised to the second power. Now, look at this overall K next to the top K and the bottom K. And I'll use a different color. Look at this portion of the overall K and see how it compares to this. And look at this portion of the K and how it compares to this. Do you see they're exactly the same? That means that to find the overall K for two reactions that you added together, remember we added these two reactions together to get this overall reaction, what did we do to the equilibrium constant from the top and the equilibrium constant from the bottom reaction? All we did was multiplied those two together, because this is the equilibrium constant from the top reaction, and this is the equilibrium constant from the bottom reaction, and we're multiplying those two together. So if we know the top reaction has a K sub C of 100, and we know that the equilibrium constant for the bottom reaction is 10, 10 times 100 is 1,000. So to summarize, if you add two or more reactions together and you want to find the overall K, you take and you multiply the K's together of the part reactions. The top reaction and the bottom reaction, multiply those together. Next section talks about how K in terms of concentrations and K in terms of pressures are related to one another. K in terms of concentrations and K in terms of pressures are related to one another. Well, there's an equation that relates these. We can say that K sub P, the equilibrium constant written in terms of pressures, is equal to K sub C, written in terms of concentrations, times RT to the triangle N, or delta N. This is for gases, because when we write gas equilibrium constants, we can write it in terms of pressures or concentrations, knowing that pressures of gases are many times analogous to the concentrations of those gases as well. And to relate the two, what we can do is use this equation to find one, knowing the other. So let's take the value they have here, find K sub P for the overall reaction. We found out that the overall reaction's K sub C was 1,000. What is the K sub P for this reaction? And it happens to be at the same temperature. I put at 298 as this one up above was. Now that's kind of an unwritten rule that the book doesn't talk a whole lot about, but K's, equilibrium constants, are only constant at a constant temperature, or at a particular temperature. If you change the temperature, you change the K, or the equilibrium constant. If you change the temperature, you change the K. And we'll look at the end of this chapter using something called Le Chatelier's principle as to how temperature changes or affects the equilibrium constant. So let's plug and chug these numbers now into this equation. We can find K sub P by typing in K sub C, which is 1,000 from up above, times R, which is 0.0821. That's in liters, atmospheres per mole Kelvin. And that's the commonly used R in this conversion factor between K sub P and K sub C, times the temperature, which is at 298 K. And then we take this whole thing and raise it to the delta N, or the change in the number of moles. Delta N stands for product moles minus reactant moles. Product minus reactant moles. And if we look at this reaction up above here, notice we have 4 reactant moles, and we're assuming that all of these are in the gaseous phase. That's something that's not written in here in the sample problems, but if you look in your book at the sample problem, they're all written as gases. Okay, and they got to be gaseous moles. So we have 4 product moles, and over here we have 1, 2, 3, 4, 5 reactant moles. So product minus reactant means we have 4 products minus 5 reactant moles. 4 minus 5 is -1. -1. So we take this and raise it to the -1 power. And if we take the 1,000 and we multiply it by 0.0821 times 298 to the -1 power, I believe we end up with a K sub P equaling about 40.87, I believe I had. And remember, no units for that as well. No units for that as well. Last part of this video cast, we're going to talk about how we can use this setup of products divided by reactants to the power of their coefficients, even though we're not at equilibrium, to help us determine what we would be at what we would need to do to approach equilibrium. This is called calculating Q, and Q is called the reaction quotient. The reaction quotient is calculated the same way K is found, where you take products to the coefficient divided by reactants to the coefficient, except that Q uses the initial concentrations or pressures, whereas K uses the equilibrium values. Q can tell us if a reaction's concentrations or pressures needs to shift from the reactants to the products or from the products to reactants. Here's how to tell with an example of A plus 2B goes to 2C plus D. If, before the reaction starts, A, B, C, and D concentrations are all equal to 1 molar. And let's assume for this that K is equal to 10, just to give us some easy numbers. Let's just say that K is equal to 10 for this reaction. Well, let's calculate what's called Q, or the reaction quotient. For this, you take products, C, I'll write it in brackets because we'll assume it's in concentrations, to the second power, times D to the first power, divided by the reactants, A to the first power, times B to the second power. And we'll put in 1 for each one of these because they're all 1 molar. So 1 squared times 1 divided by 1 times 1 squared. We end up with Q equaling 1. Well, how does this compare to K? Well, you have to remember that the reaction quotient is nothing more than a fraction. And in this case, the fraction turns out to be 1 divided by 1. Remember from math class, you can take any number and write it over 1, and that's what the number really is. Same thing with K. K is nothing more than a fraction saying that it's 10 over 1. So what's bigger, the top part of the fraction in K or the bottom part of the fraction in K? Well, we see that 10 is way bigger than 1, meaning since K and Q are both products divided by reactants, the products are bigger at equilibrium than they are right now, meaning that we will have to shift to the products to achieve the equilibrium constant, to achieve an equilibrium constant of 10. So if you're wondering which way to shift with Q once you've calculated the quotient, always write it as some number over 1, and then compare it to K as some number over 1, and ask, what's bigger, K on top or K on bottom? And you always have to get Q to look like K. This example problem right here gives us 3 scenarios where we calculate Q, and then after calculating Q, we can decide what we'd need to shift, products or reactants, to achieve the equilibrium constant. Are the following mixtures of A, B, and C at 100 degrees Celsius at equilibrium? If not, indicate the direction that the reaction must proceed to achieve equilibrium. Here's letter A. It gives us a concentration of 1, 5, and 0.1. For this reaction, A plus 2B goes to C, the equilibrium constant, and therefore the Q, or reaction quotient, would be products C divided by A to the first power times B to the second power. And we plug in the numbers that they give us. Initially, C is at 0.1, A is at 1, and B is at 5, and we need to square that. And if we take 0.1 divided by 25, we end up with 0.004. And it tells us up here in the reaction that K sub C, or the equilibrium constant, is 2.5 times 10 to the second, or you could write it as 250. So, which way does the reaction have to shift? Remember, you can write the equilibrium constant as a fraction, 250 over 1, and you can write Q as a fraction, 0.004 over 1. Well, what needs to change, the top or the bottom, to get to look like the equilibrium constant 250? Well, you can see that this is way smaller than 250. So to get Q to look like K, you need to make the top way, way bigger, which means I need to take C, which is the products, and make them bigger, so the reaction needs to shift to the products. Shift to the products. Look at it in terms of a fraction and ask what needs to get bigger to achieve K. What on Q needs to get bigger to achieve K? This was too small compared to the top, so it needs to get much bigger. Let's look at letter B and see how that pans out. Q for this is equal to products, which is 0.0001, divided by the reactants, which are 1,000 for A, times B, which is 50. And remember, that needs to be squared because it got a 2 in front of it in the balanced chemical reaction. So now if we take 0.0001 and divide it by 1,000 times 50 squared, we end up with a really tiny number, 4 times 10 to the negative 11th or so. Now remember, K was equal to about 250. Well, what needs to change to get Q to look like K? Remember, you can write both as fractions. Take the number and write it over 1. What has to happen to the top of Q to make it to look like K? Well, it needs to get way, way bigger, right? Which means I need a lot more of the top thing, or a lot more of this thing called C, which is a product. I need lots more products. And so what I need to do is I need to shift to the products. Shift to the products. Okay? Let's look, very similar to letter A, except for it was a lot smaller number. And then lastly, let's look at letter C. And in letter C, we find Q by taking C, which is 1,000, and dividing it by the reactants, which are 1 and 0.0005, and squaring that, because remember there's a 2 in front of the B right up here, and so it's got to be a power of 2. So 1,000 divided by 0.0005 squared turns out to be a really big number now, 4 times 10 to the 9th. Now we compare this number to K, and K, remember, is equal to 250. So write these numbers as fractions once again, and what needs to change about Q to make it achieve or look like K? Well, the top has to get way, 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 way smaller, which means that I need to get lots more reactants, or this needs to get a lot smaller, which is the products, and so it needs to shift left to the more reactants. More reactants. This is how Q is valuable to us in helping find which way a reaction needs to shift to achieve K.